Welcome to part 2 of implementing genetic algorithms in Houdini. In this episode, we will be trying to implement genetic algorithms using PDG and TOPS. Let's take a look at what we are trying to accomplish. With genetic algorithms, we are trying to find a solution to an optimization function, the fitness function. In our case, we want to find a geometry that maintains the volume of a box, but minimizes the surface area. In the previous episode, I implemented this using SOPs, and now let's try to do this in PDG and TOPS. Let me forewarn you, PDG does not really have any control flow elements, so our solution will be a little bit hacky, but we'll get it to work. Let's get started. All right, let's get started. Let's turn this off. Let's put down a top network. And the first thing that we have to do here is to actually generate our initial boxes. So let's put down a generic generator. Let's maybe just do 10 to begin with. And then the next thing that we want to do is really a raw geometry output. However, what is it that we want to generate here? It's random boxes to start with. So let's get these from over here. This is our box. Thank you. Let's put down a new node. We will call this random box. Let's put the box in here. And then let's get the point jitter out of the solver to get our first initial setup here. Great. The one problem that we're having here is that this random ID that I'm generating uses nRandom, and nRandom is exactly the same every single time that we call Houdini. So we have to do something that is really random, and the only way that I want to do this is with Python. And we basically want to generate this ID in Python now. So let's get a few helpers. Let's import random, which allows us to generate random numbers, and let's import OS, which will give us real randomness in terms of the stream. All right, so we want to create an ID attribute, and that is done as follows. And a point attribute, and we will call this ID. So then we want to do something for all points in the geometry. And for each of these points, we want to set the random ID. So at the point, we'll set an attribute value, which is the ID attribute. And we just make this a random integer from, let's say, 0 to 50,000. And this should be it. There's one more thing we have to do is we have actually to seed the random number generator from some operating system randomness. And that looks like so. And now if we check this, hopefully it will give us random IDs. And these random IDs are going to be different every single time that we call Houdini. All right. And then just to make it easier, let's put a null here that we call out. All right. So then we can go back into the top network, and we will call this our initial box, and it cooks the random box out. And how do we want to call this? Let's save this into a separate directory. We don't need the hip name, we don't need the frame number, but we do want the index. All right, that should be it. Let's try to cook this. Okay, easy enough. And now we have a differently shaped random box. All right, so as before, we now want to measure what's going on here. The measurement will happen also by modifying the geometry. So we call another rob geometry output, which we will call measure. This time though it's going to be slightly different. We'll be using the internal representation. Call this, let's get rid of this. So let's put the index back in. And then we want one more attribute that I will explain later. We'll just be calling this iteration. All right, so let's dive into this. And it's going to look, very similar to what we had done before. So in fact, I think we may just be able to get this from the solver as well. Let's click on one so it has some input. But let's go to the solver. And basically what we want here is the attribute to lead and all the measurement. Okay, let's click on one again. Well, it's actually generated. And then click on one. All right. So then let's plug this in. And now when we look at the detail, we end up seeing the score and the total area and the total volume, which is exactly what we wanted. All right, easy enough. And this will now happen for every single generated box. So the next thing that we need to do is we actually need to get this back into our attributes. And for that, we will use geometry import. And the geometry import with the detail. And it will not output. Instead, it will just point to the upstream result file. And we want to load geometry during the cook. And we just want to keep that index. We don't want to store this, we just really want the attribute. So let's try this and see if this works. Shift G, cooks very fast. And now we should have an attribute that hopefully has the total score. And that total score should be different for every single one that we look at. All right, and now for genetic algorithms, we want to use the top scoring ones. And so we need to wait for all the results with wait for all. This will create one partition for us, but it has a neat feature where we can sort by attribute, which is the total score, and we want descending order. So now if we cook this with Shift G, we will see that we have one partition. The measure 9 has the highest score. So let's take a look at this. This is 8, this is 9 with 0.608, and that does seem larger than all the other ones. Great. Before we start with the more complicated work, let's actually fix up the iteration. And for right now, let's just create an attribute here so that the files that we create have the appropriate values. All right, that should do it. And then for kicks, we can just run this real quick and see if the file names are right now. It's a little bit slow, but here we go. All right, now we have an appropriate file name. So we have everything in one partition now. And for genetic algorithms, we really want to consider only the top candidates and then appropriately combine them. So that means that we need to tease the items in the partition apart now and essentially select the candidates that we want to have for crossover. And we'll be doing this with a Python processor. For the Python processor to work correctly, it's important to turn the work item generation to dynamic, because otherwise it will just assume that it's static, and that will not work for us. All right, we know everything is in a single partition. So let's get to our partition items. So we really have one upstream items, which is basically the only thing that we get from the stream. And we know that we want to consider the top half of these. So let's just figure this out. Upstream items, partition items divided by half. So these are the ones that we want to iterate over. And we do this in Python really easily. We want to take the current item, which is the upstream item from the partition at our current index. And then we want to choose the next two. But before we do this, let's also keep a copy of the result data, which is just the first output here. There could be more, but in this case, it's really just the one. And then we know that the total score for this item is in the data section. It's a float attribute, so float data, and it's the total score. And since these can also be indexed, it's the first one. And for debugging, let's just print this out. It's not really terribly important, but at least we know that something is happening here. All right. So at this point, for the output, I also want to increase the iteration count. And that is why I hadn't injected it before. Okay, let's take this. And if it's not defined, we just set it to 1. But if it is defined, then we just increase it. All right. Because we also want to keep track of our status, for this iteration, let's just keep the best one and output it separately. So this is fairly easy. We can just create a new item via the item holder and add work item with an index of 0. And then we want to keep track of the iteration count, which is iteration that we just created. In this particular case, we also want to set the attribute best, which we just used to remember that this was the top scoring item from this particular iteration. And then we also keep track of the score, total score, which we saved up there. And then of course we also want to keep track of the result data, and so we just add this back. There might be a better way of doing this, but this is what seems to work. All right, so now later on we can just filter on the attribute best to take the best one from the current iteration. And now we want to cross over with the next two. And so we index back into the partition, which is the upstream item, partition items, add a plus j, and because this goes from 0, we have to add 1 on top of it. And we also keep track of this result file, because we need to add it into our work item, and this is the result data. Great. So now for this particular pairing, we want to create a new work item, and I think we can just copy most of it from up here. Just have to make small changes. So the index needs to be changed. That is essentially 2 times I plus j plus 1, so it starts counting at 1. The iteration is correct, but this is not the best result. The total score doesn't really make sense to save here, because we don't have a total score for this one yet, and there are 2 different ones. And we now also need to add the result file from the other. And I think this should be it. And let's just call this candidates for crossover. And let's run this and see what happens. Hopefully we don't get any errors, but we probably will be getting some. Yeah, there we go. Probably some typo. List object has no attribute partition items in line 3. Ah, this is the upstream item. Let's try this again. And another error. Seeing this, I think it might tell us that we actually don't have the score in here, but we should have the score. Oh, it's not called total score for some reason. Okay, let's look at the measure here. Compute score. And it looks like I may have forgotten to make some adjustments. This can be done much more easily now, because basically we just need to store, don't need any of this, and we just need to output total score, delete all results from disk, dirty all, and let's just run up to measure and see if we get the results that we want. Oh, we have to run the geometry import. There we go. Okay, now we do have a total score. And then let's run this too. Great. And now let's try this. That does not look so great. Let's figure out what's going wrong here now. Has no attribute partition items in line 22. Partition items. All right. And now we do get the output with the highest ranking scores. But after some more debugging, I figured out this was because of wait for all, where we ask it to merge the input attributes. So we don't really need this here. And let's call this wait and sort scores. And now if we regenerate this, this should give us better data. All right. This looks much cleaner. And now what we can do is actually do the crossover work. But before we do this, just for giving us a way to look at our progress, let's split out the attribute that gave us the best result. And we can just do this by best. On the left hand, we will have the one result. And on the right hand, we will have the items that we want to have for crossover. And in order to compute the crossover, we will do a geometry output. And we will name this, get rid of the hip name. Let's remember the iteration. And then also the index. And I always do this, accidentally pressing the escape key while blindly typing. Let's try this again. Iteration, PDG index, and that should be it. We will not use an external sub, and instead we will dive right in here. This is do crossover and rotation. All right, let's construct the crossover here, which is going to be fairly simple. So we know that we have two incoming files. So let's get the other one, which is pdg input 1. And then we want to randomly choose one of them based on the mutation rate, which we will do with an attribute wrangle. Actually crossover rate, so this is crossover. And before we can do this, let's actually select one of these results. Actually, let's generate this. click on it and then dive in here. All right. So as I mentioned before, this gets run on a fresh Houdini start. So we need to have a way of generating random numbers. Fortunately, we already figured this out here with this Python node. Let's actually call this random ID. So we'll just be reusing this, and we'll be sticking a random ID just into the point attribute. We don't need to create the attribute. We know it's there already, and instead we will just be setting it here. All right, now this is happy too. And then the crossover becomes actually fairly straightforward. So we want to get our crossover rate, which is just the channel. Crossover. And then we want to generate a random ID, which we will generate from the randomness that we have there already, plus some other number. And if this is in our crossover chance, then we will just be setting the point from the input geometry that we get in the second input. And this is crossover. Fairly straightforward. And the mutation will sort of happen in a similarly straightforward way. Actually, let's do a new attribute wrangle. Which we also do black. Mutation. What's the chance of mutation, which is another channel. And then if our random number maybe is smaller than our mutation, then we will do something special here. And we will generate another random number because we like it so much. And similarly as before, this is going to be a vector that goes from negative minus 0.5 to 0.5. And we scale this. We might want to make this configurable, but that is good enough for now. And then the mutation rate is going to be much smaller than what we have done for the crossover. And then last but not least, we will also smooth this again to keep the primitives a little bit orderly. And this is basically it. So let's try to generate this and cook it. And there is our output. So we can try to take a look at this. And that looks quite reasonable. Great. So now the trick here is, how do we turn this into something that we can run over and over again? And unfortunately, PDG and TOPS, even though they have a for and feedback loop, they don't have any control structures. So with a for loop with feedback, it's actually not possible to do it in here, first and foremost, because you can't wait on a single iteration. So this doesn't work, but there's something else that works. And it's a little bit hacky. But it basically goes like so. We can create subnetworks in PDG. And if we look at the measure and crossover and put this in a subnetwork. Oops, that's not what I wanted. Let's call this one iteration. And we want outputs here. Output 1. And another output. All right, there we go. then we can just repeat this over and over again. So let's do a few of these. And we want to connect to the second output, and the second output. And then remember, the first output gives us the best result from that generation. So we can just merge this all in. Oops. And let's figure out what it is that we're actually displaying here, which is probably not what we want. It's actually show the box, which is just going to be a file on the PDG output. And now we can try to run this, and hopefully this is going to work. Let's actually kill this. This seems broken. And let's get a new scene view. All right, this is better. The first one, the second one, the third one, and the fourth one, which look awfully similar. 0.84 and 0.81, so fairly close. Let's apply this to a more real example. Here I have a top network that simulates the growth of a tree. And the problem for the tree simulation is that there are a lot of different parameters that influence it. And usually you would want to wedge this, but wedging doesn't really have any intelligence built in. So instead here, I sort of selected a few parameters like light A and light B, or kappa and bud angle and tropism weight, and I'm trying to use genetic algorithms to select the one that gives me the most interesting tree. And let's look at what I mean by most interesting tree. And this happens here in the make tree node. And basically what I do here is I tetrahedralize a very simple polywire tree and then measure the volume. And the volume is essentially what I take as the interestingness of this tree. And the more volume that the tree has, the better it has grown. And otherwise everything is pretty much the same. Crossover is slightly different because we now have to do crossover on the different attributes. But in terms of the Python code, the principle is quite similar. So we do crossover on the different values from the float data dictionary here. So let's try to run this and see if it actually gives us more interesting trees. And this will probably take a few hours to run, just because the simulations are fairly long. And I'll be back when they're completed. After roughly 2 hours later, we got 6 iterations computed. And if we take a look at the values, we see that the total score here was 11,800. Here the total score was 11,000, 11,100, and 11,900. So interestingly enough, we did not really converge on a much higher score. But let's take a look at what kind of results we got. And I fear that Houdini just crashed on me. After restarting Houdini, I decided I would just render the trees so we could take a look at it. They are not particularly interesting, but I think this is nonetheless a good example for seeing how to use genetic algorithms to quickly find plausible parameters for a simulation, and then traditional wedging may be able to use to really fine-tune it. I hope you enjoyed this, and I may record a few more of these. Bye.